Hey guys, welcome. If you are one of those who's looking to get started with data engineering on AWS, then you are at the right place. In this video, I'm going to summarize all the AWS services in a typical data engineering tech stack so that you have a clear overview of what should you be focusing on when it comes to building ETL pipelines or even setting up a data stack on AWS. So what's the objective here? Firstly, you will immensely benefit if you are a beginner and looking to find a job, or if you have an interview in a data engineering profile focusing on AWS. Secondly, the idea here is to cover at least 80 to 85% of typical data engineering services and flows on AWS, so that if you're planning to learn or take up AWS courses, then you already know which AWS service is meant for what purpose. It would also help you if you can take notes for reference purposes, so that it'll help you later on. So let's begin by understanding the definition of data engineering. In simplest possible words, data engineering is the practice of designing and building systems for collecting, storing, and analyzing data at scale. And this principle applies across the board, regardless of the underlying tech stack or cloud provider. So you collect data from the source, transform the data if need be, and then you store it in the destination system. Once your data is available in the destination system, it can be used for a plethora of purposes such as BI reporting, data analytics, or even data science. Now, coming to the systems that can possibly store the data or act as a data source on AWS from where you need to extract this data, I believe it's safe to say that 99% of the times you will have your source data in one of the systems that you see on the left-hand side. Your data could be in a relational database like MySQL or PostgreSQL on AWS, which is also called RDS on Amazon Cloud. RDS lets you spin up all possible relational databases such as MySQL, PostgreSQL, SQL Server, Oracle DB, which is a managed service offering. Now, a managed service means you set up the servers with the required software or installations, and AWS takes care of the ongoing maintenance, scaling, and management for you. Next, you have NoSQL databases like Mongo and DynamoDB. DynamoDB again is a NoSQL data store which is managed by AWS. So if you want to store NoSQL data on AWS, you can just start using DynamoDB right away. You have S3, which offers a storage layer and also serves as a data lake on AWS. And Redshift is a data warehouse service which lets you run analytical SQL queries to transform and analyze your data efficiently. Kinesis and Kafka provide streaming data solutions, with AWS Kinesis being a managed service directly offered by AWS. And Kafka is available on AWS as a managed service as well. It's called MSK, which stands for Managed Streaming for Kafka. Finally, you have external APIs, which are deployed outside of your ecosystem, via which you can fetch the necessary data. So that list pretty much covers almost all sources of data on AWS. Of course, there could be a couple of similar systems that's not on the list. Now, let's move on to the possible destination systems where you might store the data depending on the use case. So if you think about it, the destination systems don't look any different than the sources. It's the exact same list where your source is one of these systems and your destination is also one of these systems. You can pretty much do a crisscross with all possible combinations of sources and destinations. Also, there'll be often times when your source and destination systems are one and the same, which is a pretty usual scenario. So in a sense, data engineering can be segmented into three main areas. You have batch data processing, which focuses on handling large volumes of data at scheduled intervals. You have real-time data processing, which deals with data as it arrives, enabling immediate insights and analysis. And finally, you have event-driven data processing, which triggers specific actions in response to particular events, which allows for responsive and dynamic data handling. Now, it's your responsibility as a data engineer to understand the requirements and choose the right AWS service depending on which area the use case falls under. And in order for you to be able to do this, there are certain factors you got to keep in mind. So with batch data processing, we're dealing with mountains of data. And to manage this efficiently, the process is spread out across several systems, focusing on high throughput in a distributed fashion. This means we can chew through massive data sets effectively. But here's the twist. Speed isn't our top priority when it comes to batch data processing pipelines. We're not racing against the clock for instant results because by nature, batch processing takes its own time to ensure thoroughness over instant results. With real-time data processing, we're aiming for lightning-fast insights where the processing happens almost as quickly as the data arrives. It's all about staying nimble, handling bite-sized chunks of data for instant analysis. But as you might guess, the speed comes with its own challenges. Setting up a system that's constantly on its toes, integrating data on the fly, this kind of cranks up the complexity. With event-driven data processing, the architecture is highly scalable, meaning it's designed to handle tasks of any size seamlessly. Event-driven pipelines work efficiently, dealing with events as they happen, without wasting any resources. With event-driven architecture, the integration with various data sources, specifically AWS services, is extremely smooth, and most importantly, this approach is cost-effective because of the pay-per-use model, where you only pay for the resources that you actually consume. On this note, let's jump into the AWS services for batch data processing. First off, before choosing any service, you gotta ask yourself, is my data really big? If the answer to this question is yes, you're looking at heavy data lifting. In this case, you have Spark. And you have 3 AWS services that can run Spark jobs, be it Scala or PySpark. First, you have AWS Glue, which is a serverless data integration service that not only handles integration and ETL, but it can also kick off Spark jobs. Next, you have EMR, which is Elastic MapReduce. It's a service meant for big data processing with services like Spark, Hadoop, and other data frameworks which come pre-installed. All you have to do is check a specific box to ensure that service is installed at the time of spinning up the EMR cluster. Next, you have EKS, or Elastic Kubernetes Service, which lets you run containerized Spark applications with the power of Kubernetes. But what if your data isn't big? Well, for small-scale data processing using Python, Pandas, PyArrow, there's a whole lot of services to handle that. First off, you have AWS Lambda for short-lived serverless computations. And if you need more control, you have EC2 instances, which are nothing but virtual machines on AWS Cloud. You have AWS EKS, which is still in play here for containerized orchestration. AWS ECS, which is Elastic Container Service, which manages containerized applications without the overhead of managing a cluster. Again, you see AWS Glue here because Glue has a variant called Python Shell for simple, lightweight Python scripts, and it comes pre-installed with a whole lot of libraries such as Pandas, PyArrow, scikit-learn, PyMySQL, and many more, which come pre-installed and can be extremely handy. Finally, you have AWS Fargate, which is a serverless compute engine for containers, or Docker containers, let's say, which removes the need to manage servers and clusters. But there's another layer to this, which is orchestration. If your pipelines need orchestrating, and if you're seeking an automated workflow for these services, you have 2 options. You have AWS Managed Airflow, which spins up an Airflow cluster. And by Airflow, I mean Apache Airflow that you guys might be familiar with, which acts as a managed service here. And it takes away the overhead of setup and maintenance. Next, you have AWS Step Functions, where you can coordinate multiple AWS services into serverless workflows, enabling you to build and update applications quickly. So by understanding your data size and the complexity of your workflows, you can make informed decisions on the AWS services that best fit your batch ETL needs. Now let's focus on scenarios where your source and the destination are one and the same, which is quite a normal scenario. Imagine you have massive amounts of transactional data sitting in Redshift, and you want to transform this data, aggregate them, and write them back to Redshift so that they can be used by Quickstart or Tableau or any downstream BI tool out there. Or maybe you have a data lake on S3, which has raw data in its original form, and you want to transform this data and write it back to a different S3 bucket. These scenarios are quite common, and I've seen a lot of times data engineers just deciding to use PySpark to transform data sitting inside of Redshift and writing it back again to Redshift. Now, this isn't a wrong approach, but you must realize one thing which is very crucial. Let's say you have 10 GB data to be batch processed in one go. In this case, your PySpark job running on EMR or AWS Glue will read this 10 gigs of data first and hold it in memory, and then perform the transformations before writing it back to the same system, which is Redshift in this case. Now, there's something called push down predicate in Spark which can help with this scenario, but overall, this approach is going to make your pipeline slow and it's going to cost you. But like I said, this approach is fine if PySpark is the only option you're comfortable with. In general, I follow a thumb rule, which is if there's vast volumes of data sitting in Redshift and you need to transform and aggregate them, then my first option is to write advanced SQL queries in Redshift itself, because we're not moving the data outside of Redshift, and this is very optimal. But of course, you will probably end up writing hundreds of lines of SQL code depending on the transformations. And as much as possible, I try to stick with this option. Now, for whatever reason, if the transformations are not possible via plain SQL or advanced SQL, and it requires a scripting language, then we can always use Python or PySpark running on one of the services we've already seen before. The same goes for S3. You have Athena, which lets you run advanced SQL queries against the data residing in your S3 storage, which is your data lake. All you need to do here is set up a glue crawler, which will pass and scan all of your data, which is sitting in S3, and infer the schema. And once the schema is ready in your glue data catalog, you can run SQL queries using Athena against this data. Redshift Spectrum is a feature of Redshift, which lets you run SQL queries against the data residing in S3 inside of Redshift. Similar to Athena, but you can access all of this inside Redshift as opposed to Athena in this case if you use Redshift Spectrum. Finally, you always have the option of using Python or PySpark in order to read the data from S3 and write it back to S3 in a transform form. Now let's talk about the services involved in an event-driven data processing architecture. So to begin with, how do you define an event? An event is basically a signal that something significant has occurred within a system or an application. It's basically a notification or a flag raised by a user action or a system that tells other parts of the systems to kick into action. For example, a customer buying a product on your website or your mobile application. Similarly, a failed transaction or a user resetting their password. Stock updates happening in your inventory or ERP systems, or it could even be a file containing a few hundred rows or transactions which is being uploaded to your S3 bucket. All of these are events. Let's take an example of an e-commerce website where customers are purchasing products, and as soon as the transaction is successful, the application sends a payload containing the customer ID, the product ID, the amount paid, and the transaction date. This payload will be written by the producer application into Kinesis or Kafka inside a specific topic. Now your objective is to take action on this event. In this case, you want to send an email notification to that specific customer informing them that they have successfully made the purchase. Another example is a file being uploaded to your S3 bucket. Let's say there's a third-party vendor sending details about web analytics in a JSON file every day between 6 and 7 a.m. As soon as the file is uploaded to your S3 bucket, you want to ingest this data into Redshift or DynamoDB for further analysis. Now, considering such use cases, you have a bunch of services that can come into action depending on the business needs and requirements. First off, you have AWS Lambda. This is a serverless compute service that we know that can spring into action in response to events such as an S3 object upload or a payload being written to Kinesis. Lambda can execute custom code to process these events, making it an agile responder in an event-driven architecture. Next, you have AWS Step Functions, which allows you to orchestrate microservices, distributed applications, and serverless workflows. With Step Functions, you can design and execute complex workflows that react to events, ensuring a seamless progression of tasks across different services. You have SQS, which is Simple Queue Service, which can act as a message queue that decouples and scales microservices, distributed systems, and serverless applications. It can buffer and manage the communication between the different components of your architecture, ensuring none of your systems are overwhelmed by a sudden influx of events. And finally, you have SNS, which is Simple Notification Service, which is basically a pops-up messaging service that's all about getting the word out quickly and efficiently. With SNS, you can fan out notifications to a large number of subscribers, and by subscribers, I mean downstream applications, such as sending that purchase confirmation email to customers. In this case, your email system is a subscriber, right? or it can trigger a series of Lambda functions as well for complex data processing. To summarize, for big data batch processing, you have EMR, Glue, and EKS, which can run Spark or PySpark jobs in a distributed fashion. If you want to run any specific Hadoop framework like Scoop, that's available in EMR as well. And these pipelines can be orchestrated using AWS managed Airflow or step functions. Now, if your workflow does not need any heavy lifting, meaning if you need simple Python jobs with Pandas, PyArrow, scikit-learn, PyMySQL, and so forth, then you can use AWS EC2, Glue for Python shell jobs, ECS and EKS for those as well, and the orchestration frameworks remain the same. For real-time data processing, we have managed Kafka and AWS Kinesis as streaming services on AWS. To process this streaming data, you can have PySpark streaming jobs running on Glue or EMR. Kinesis Firehose is also a good option, but only works if your streaming data is inside Kinesis, or if you're using Kinesis as a streaming solution. And then you have Flink jobs running on EMR clusters. For the sinks, and by sink I mean any system where you write the data to, 95% of the times you'd write the data to Redshift, S3 Bucket, DynamoDB, or even MongoDB. And finally, for event-driven data processing, you might have events written into Kinesis or Kafka topics or even S3 buckets, like I explained before. And to process them as soon as the events occur, you'd use Lambda oftentimes because it's very economical. Firehose is also a great option if you're using Kinesis. And then you have Flink running on EMR, which is also a great solution. For sinks, you would write stream data into any of these systems depending on the use case. So that was it. Hope this video helped you get a good grasp of the different AWS services for data engineering. Thanks a lot for watching.